In this video, we're going to continue developing the linear regression model. And in particular, we're going to come up with a cost function that we'll use to fit the parameters of the model. And this is what will give us the straight line that linear regression will use to predict the prices of new houses or what have you. So you remember from the previous video, we had a training set that looked like this, in which we were given the sizes and the number of bedrooms in say 47 houses in our training set, and we said that we would represent a hypothesis using this sort of linear or well, in linear regression we said that we'll use this representation, this sort of linear representation for our hypothesis, where we can write this as also theta transpose x, where by convention x0 was this new feature we introduced that's always equal to 1. So these numbers, theta i's, are called the parameters of the algorithm, and what I'd like to do in this video is talk about the problem of how to choose these parameters theta I. In particular, given a training set like we have, how do we decide what values of theta I we want? Well, one reasonable thing to do is to let's make our hypothesis h of x, or x subscript theta of x, let's make the output value h of x close to the observed value y, at least for the training examples. Okay? So just remember the notation, right? Y is the value we're trying to predict, this is the price of the different houses, and h of x is the value that our hypothesis predicts on a certain input x, on a certain input size, or size in number of bedrooms. And in particular, one way we might choose the parameters theta is if we minimize, so minimize over theta. Let's see, and I'm going to sort of keep on fleshing out this equation. So we might minimize over theta, h of x minus y. I'm going to fill this equation in as we go along, right? So we might say, try to minimize this sort of squared error term, in which we might want, the prediction of a hypothesis minus the actual price to have small squared error. And in particular, we have m training examples. So let's sum over I equals 1 to m, sum over my training set of my error on my different training examples, right? Where, again, you remember my notation is that xi comma yi, this is the ith training example. Okay? So this is my average squared error, 1 over m, of sum over all my training examples of this squared difference between what's predicted by my hypothesis and what was actually observed to be the price of the house in the ith training example. To simplify this, to simplify some of the later math, I'm going to put a 1/2 there. So minimizing 1/2 of the average squared error, should give you the same answer as minimizing the average squared error. So to simplify my math a little bit, and just to take this whole thing, take this whole term, and give it a name. I'm going to define j of theta to be equal to this whole thing, right? So defining j of theta to be this cost function, that's meant to be an equal sign there. And so the way I'm going to choose my parameters theta is I'm going to minimize as a function of theta this cost function j of theta. Okay, where j of theta is that term up there, 1/2 1 over m, sum from I equals 1 to m, that thing we've written up there. Okay. So, and by the way, I realize some of you may have seen this sort of least squares cost function, or may have seen linear regression or ordinary least squares before. And what we're going to do in the next few videos is derive a couple different algorithms for solving this minimization problem, for actually finding the value of theta that minimizes this. And later on, we'll actually generalize this least squares model to deal with nonlinear problems as well as classification, rather than only regression problems as well. to gain a bit of intuition about what least squares is doing, we said that the formal hypothesis was h of x equals theta 0 plus theta 1 x. And as you vary these parameters theta 0 and theta 1, you get different straight lines. So for example, if this is, I guess, the size of a house and this is the price of a house, you know, then maybe if you choose theta 0 to be 0 and choose theta 1 to be 5 or something, it's a totally made up number, right? And this green line is maybe, you know, the plot of 0 plus 5x. It should pass through the origin, of course. Whereas if you were to choose a different value of the parameters, you know, if you were to choose, say, a different value, such as, you know, 25 plus 2.5x, right? Then maybe you get a different line like that. And if you were to choose an even different value, like 50 plus 0x, then you end up with, just say, this is meant to be a fat horizontal line. And so, as you choose different values of theta 0 and theta 1, you get different lines. So the goal of linear regression is, right, when you have a training set, like so, in order to, what we would like to do is choose the parameters that correspond to a straight line fit to the data that minimizes the squared error, or that you know, gives a reasonable fit to the data. And in particular, written out formally, we're going to choose the parameters theta that minimizes our cost function, which we defined earlier as, excuse me, I'm going to continue this on the next line. This sort of sorry about breaking up the two lines there, but in particular we want to choose theta to minimize the squared error, and hopefully that will correspond to a good straight line fit to our data.